determining the Planck constant using a halogen lamp. In December 1900, in a meeting at the German Physics Society, the German physicist Max Planck announced that he'd been able to precisely fit the experimental data of the so-called blackbody radiation spectrum. To do this, he assumed that the energy from electromagnetic radiation was emitted or absorbed by matter in discrete packets called quanta. The energy of each quantum, for radiation of some frequency nu, was given by the product of h and nu, where h was an experimentally determined constant, now known today as the Planck constant. This quantum hypothesis constituted the first stone laid in the construction of quantum mechanics.
Firstly, let's explain what the blackbody radiation spectrum actually is. At any temperature above 0 Kelvin, all bodies emit electromagnetic radiation. The radiation spectrum of a body refers to the representation of the radiance or power emitted by the body per unit of wavelength and per unit of surface as a function of the wavelength. A black body is an ideal object that absorbs all radiation incident upon it, hence the name. In other words, a black body is a perfect absorber of radiation. According to Kirchhoff's law, for an object in thermodynamic equilibrium, its emissivity is equal to its absorptivity. Therefore, a black body in thermodynamic equilibrium is also a perfect emitter of radiation, which is to say that its radiance is the maximum possible for any given temperature and wavelength. Thus, the black body radiation spectrum is continuous and depends solely on the equilibrium temperature of the black body.
Towards the end of the 19th century, the blackbody spectrum became the subject of intense theoretical and experimental study, using real objects that approximated blackbody behavior. Although a theoretical expression for radiance was unknown, other laws were deduced, such as the Stefan-Boltzmann's law for the total power radiated by a blackbody. This power P, for a temperature T in Kelvin, is given by where sigma is the Stefan-Boltzmann's constant and S is the surface area of the body. From an experimental perspective, an example of a blackbody is the interior of a cavity whose inside walls perfectly reflect all incoming radiation, which only reaches the cavity via a small hole. This way, practically all of the external radiation that enters through the hole remains trapped inside the cavity via successive reflections. Therefore, any light that does escape back out of the cavity via the hole has an approximate blackbody spectrum. This spectrum corresponds to the equilibrium temperature T between the cavity walls and the internal radiation.
An example of a blackbody spectrum is the cosmic background radiation, whose peak intensity falls in the microwave region, corresponding to a temperature of 2.74 Kelvin. Another example, though approximate, is the radiation spectrum of the Sun's surface with a peak intensity in the visible wavelength region corresponding to a surface temperature close to 6000 Kelvin. Planck demonstrated, based on the quantum hypothesis, that for a black body, the radiance, that is the power emitted by the body per unit of wavelength and per unit of surface for a temperature T and a wavelength lambda, is given by where K is the Boltzmann constant, C is the speed of the electromagnetic radiation in a vacuum, and H is Planck's constant.
In general, for a real object, the radiation spectrum depends on the body's chemical composition and its geometric structure. This causes the emissivity to depend on both the temperature and the wavelength. However, there are so-called grey bodies whose radiance has a shape similar to that of a black body, but scaled by an emissivity coefficient whose value, independent of temperature and wavelength, lies between 0 and 1. Explicitly, where epsilon is the emissivity coefficient. The total power radiated by such bodies, at temperature T in Kelvin, is given by
An approximate example of a grey body spectrum is the radiation spectrum emitted by the incandescent tungsten filament in a halogen bulb, like this one. We'll use the simple experiment setup to determine Planck's constant, based on the radiation emitted by the filament for a wavelength in the visible region. A halogen bulb is preferable because the filament temperature is higher than that of a regular bulb for the same electrical input. This results in a greater proportion of visible light compared to infrared radiation. Now, let's explain the setup. The halogen bulb is subjected to an AC voltage, which can be varied with the voltage regulator. We measure the applied voltage with this AC voltmeter. We also measure the electrical current passing through the filament with this AC ammeter. Of the radiation emitted by the filament passing through this diaphragm, we isolate the component at 578 nanometers wavelength using this interference filter. The filtered radiation of this wavelength hits a photodiode, a device that produces a direct current proportional to the radiance it receives. This current is converted into a direct current voltage by a circuit containing a resistor connected in parallel to the photodiode housed behind this cover. This voltage is measured with a direct current voltmeter. Let's assemble the components. First, we can attach the filter. If we turn off the bulb, we see that the direct current voltmeter reading is non-zero. This is due to ambient light entering. To block it, we can shield the filter and photodiode with a cover. Now, when the diaphragm is placed right in front of the opening, we can check that the direct current voltmeter reads 0. Now, let's turn the bulb on. To maximize the incident light on the filter and photodiode, we move the diaphragm until the direct current voltage reaches a maximum. This fixes the position of the diaphragm and bulb for measurements at different voltages from the regulator.
Here is a diagram of the entire setup. Let's see how, using the measured AC voltage and current and the DC voltage, whilst ensuring the diaphragm and bulb are spaced far enough apart such that the photodiode's response isn't saturated, we can determine the filament temperature and thus the Planck's constant. To determine the temperature, we use the known relationship between the tungsten filament's temperature T and its electrical resistance R, where T0 and R0 are reference values, for example, room temperature and the resistance at that temperature, and gamma is a numerical coefficient, and R is given by Ohm's law, where V and I are the measured AC voltage and current. Though the value of gamma can vary for different temperature ranges, we'll assume an effective constant value from room temperature up to the maximum operating temperature of the filament. To determine this effective value, we take into account that, after a short operating period at a given voltage, the filament's temperature remains constant, in such a way that all electrical power consumed by the filament is emitted. However, not all of this power is emitted in the form of radiation. For instance, in a halogen lamp, gas convection occurs inside the bulb due to the temperature difference between the bulb surface and the filament.
In fact, the power radiated is only a fraction of the electrical power, which is to say that, where A is a constant between 0 and 1. We can therefore write, where capital A and B are constants, and taking natural logarithms, we obtain. So by plotting the natural logarithm of V multiplied by I in watts against the natural logarithm of V divided by I in ohms, we obtain a straight line with a slope for gamma. From the value of this slope, we calculate gamma, which turns out to be 0.86. This value of gamma, along with the measured values of room temperature and resistance at that temperature, allows us to determine the filament's temperature range. For AC voltages between 100 and 220 volts, The temperature ranges between 2100 Kelvin and 3000 Kelvin.
To determine Planck's constant, we also use the measured DC voltage, which we know is proportional to the Planck radiance. Which is to say, where D is a constant of proportionality. We assume that in the filament's temperature range, below 3000 Kelvin, we can approximate that, such that, where capital D is a constant. Taking natural logarithms and substituting the expression for temperature, we obtain. Thus, by plotting the natural logarithm of the DC voltage expressed in volts against R in ohms, raised to the power of negative gamma, we obtain a straight line of slope. Using the obtained value of this slope, and using the known values of the velocity of electromagnetic radiation in a vacuum, c, alongside the Boltzmann constant, k, we calculate h. The calculated value is 6.4 times 10 to the negative 34 joule-seconds, which is very close to the experimental reference value of. In fact, an analysis of the percentage error yields an error of approximately 5%, which makes it compatible with the literature value. We can, finally, verify numerically that the applied approximation is consistent, and for filament temperatures below 3000 Kelvin, we have.
In this video, we have shown how Planck's constant H can be determined through the analysis of the radiance of an incandescent tungsten filament in a halogen bulb.
This constant, which plays a central role in quantum physics, represents the fundamental quantum of the physical quantity known as action. We can say that the study of a system requires quantum physics when its action is not much greater than h. Despite the simplicity of the setup and the approximations made, the value obtained for h confirms the suitability of the method we used for this experimental determination.